So this time we're going to talk about a conservation of energy problem in which there is work being done. In other words, the total energy of the system does change due to a force imparted by some outside entity, which in this case is actually in a way kind of an inside entity, but it's due to the thrust involved in a rocket. Now this is from chapter 11 in your textbook. It's an example that's done there, but in the solution that they give there, they end up going about this roundabout way of talking about the work being done by such and such force, the work being done by such and such other force, and I think that's actually relatively confusing. Now, they eventually discuss why they talked about it that way, and then come up with the better way of doing it later on in the chapter, but I think it's better just to introduce the better way to begin with. And that's the idea that work is the change in the total energy of the system. And that's how we're going to approach this problem. And by total energy, we're talking about not just the kinetic energy, but also the potential energy that is due to various conservative forces. Whenever there's a conservative force, you can dictate a potential energy that is involved in that. And that's what we have already done before in talking about gravitational potential energy. So here is the problem. A 150,000 kilogram rocket is launched straight up, where the motor generates a thrust of 4 million newtons. The question is, what is the rocket's speed at a height of 500 meters? And ignoring air resistance and slight mass loss. Now, we could solve this problem using kinematics and Newton's laws. It would not take incredibly long, but it would take longer than solving it this way. So we're just going to solve this using energy conservation. So we're going to write our givens. Initial height and initial velocity are both 0. Final height's 500 meters. We're trying to find the final speed. And the force acts over a certain distance, which we're going to call delta r. Sometimes you'll see the distance called d. I'm going to call it delta r here. Either way is really fine as long as you know what you're talking about. But that delta r is actually 500 meters, the change in the height, or in other words, calling the initial height 0, final height 500 meters. So here's where we go about conservation of energy. In this case, the force adds energy to the rocket. So work is being done. So this is our general conservation of energy statement. We have this work added in. We could have added that in problems before and just called it 0. A lot of people recommend doing that. When I teach AP Physics 1, I do recommend doing that. Hopefully you all are not confused with when we add in work, when we don't. You could just think of it as always adding in the work, just a lot of times it's 0. This time it's not, because there's this extra force here from the rocket's thrust. So here's where we stand. What are our total initial and final energies? Well, just like before, we draw an energy bar graph. And here we go. Notice this time it starts off not moving with no height, so there are no kinetic or gravitational potential energies initially. And there aren't any springs, so there aren't any elastic potential energies either initially or finally. If there were, then we'd have another column here with bars, initial and final. But there is work being done by the motor of the rocket. And the end result of this is that the rocket ends up gaining some kinetic energy and ends up gaining some gravitational potential energy. Whether the relative heights of these bars are correct, I have no idea. The point is that the total height between the kinetic and potential final is equal to the amount of work that was done, plus whatever was there initially, which there was nothing in this case. That's what's important. So we now see that our conservation of energy equation becomes like this. And again, there are no other potential energies to be added in. If there were springs, then there would be. In this case, no springs. So a couple of these things are 0 because it's not moving initially and it starts at the ground. So we were able to get rid of a couple of terms. And we're solving for this final speed of the rocket. So here's where we are right now. So we're going to subtract mgh final from both sides, and then we're going to multiply both sides by 2 and divide both sides by mass in order to get this final velocity squared by itself. And then we're going to take the square root of both sides to really get it by itself. And now it's time to plug in some numbers. And upon doing that, and shoving them into a calculator and turning the crank, listening to it grind and whir, we get a final speed of our rocket of 130 meters per second. That's what we were after. That's how you solve problems like this using conservation of energy where work is being done by an external force. Thank you.